Panel. This week's panel discussion focuses on Phil David's advocacy of a parsimonious approach to causal inference. Parsimonious because it avoids assuming the existence of a definite value for outcomes of experiments that are not performed. Our panelists are Phil David himself, emeritus in statistics at Cambridge, Ilya Shipster in computer science at Johns Hopkins, Thomas Richardson in statistics in Washington, and Sylvia Winmakers in philosophy at KU Leuven. The purpose of our panel discussion is to introduce philosophers to a debate that hasn't received much attention in the philosophy literature. So I especially want to thank Sylvia for undertaking to present a philosopher's perspective on something that the philosophers have not chewed over so much. Our other panelists, Phil, Ilya, and Thomas, are familiar to the topic, and I think it's fair to say that they have debated it in the past. I hope that today will not be a continuation or just a repetition of debates they've had in the past, but it will be an effort to explain the issues to those who might not have seen them before. And in particular, I hope we'll hear some attention to one of the questions that I posed in the announcement of the panel, which is, what are the obstacles to the adoption of Phil's viewpoint? It's something that's been discussed for 20 years. Why can't we do it Phil's way? Or why hasn't that been popular among statisticians? So Phil, we're going to try to keep each, as you know, each panelist to 10 minutes, so it's all yours.
Thank you very much, Glenn. I'll try and share my screen. Let's hope it's going to work. You've disabled screen sharing, so please do something about that.
Sorry about that, my fault. Let me just.
Sorry.
Okay, can you try now? It should work now.
Okay, let me try now, and let me see if I can find the right screen to share. Let's try this. Okay, good. Can you see that?
Yes.
Good, splendid. Okay. Well, thank you, Glenn, very much indeed for this opportunity to showcase these ideas, which doesn't come very often. You did say that the statisticians on the panel have discussed this in the past. Actually, we're also discussing it in the present and future. So I'd like to point out that I had a recent paper in the Journal of Causal Inference, and both Ilya and Thomas will have discussions of that paper, which are due to appear in the journal in due course. Coexisting potential responses, do they exist? Are they useful? Let's just recall the questions that Glenn set for the panel and have a quick look at those. I'll come back to those at the end with my answers, most of which are very brief. Okay, so let me just start by, I'm going to be as concrete as I can. So let's start with one of the very simplest possible decision problems. Here, it's been a hard day. I didn't sleep very well last night. It's quite late at night for me, actually, and I got a headache. So should I take aspirin, which I typically would, but don't always? I'm wondering, is it a good idea? Would it cause my headache to disappear? So let's formalize that with a couple of variables. There's a variable which denotes the decision I'm contemplating and might end up taking, which is the number of aspirins I take, either 0 or 1. I marked it in red to denote that it's not a random variable, but a decision variable over which I have control. But there's a random variable, which is how long my headache will last. And at the moment, I'm uncertain about that. And my simple approach to this is using data. Certainly this is easy with experimental data, and under certain assumptions possible with observational data. I can assess the distribution for how long my headache will last under the two possible actions I might consider, whether I do or don't take the aspirin, because I can maybe look at data on people who did and didn't take aspirin, how long their headaches lasted. So I have two distributions. I call them hypothetical distributions because they're based on the hypothesis that I do or don't take the aspirin. But in either case, I can assess those distributions. And there are many ways of comparing those distributions. The simplest one might just be to compare their means, and we can call that the average causal effect, ACE, or in the decision context, if I have a utility attached to Y, how long my headache lasts, then I could do the difference of expected utilities, and I'd go, depending on that, I would go with whether it's positive or negative, I'd go with X equals 0 or X equals 1. Somebody's entered the waiting room and is waiting to be admitted. Can I do that? I will admit. There we go. And I can't, can I go on? I seem to be stuck here. Oh, no, there we go. Okay, so that's what I say is a very straightforward and simple approach, very ancient. Sure, it goes back before Fisher, but certainly Fisherian, if you like. But there's another approach which has become popular over several decades, many decades now, called the potential outcome approach, PO. And instead of imagining a single variable which has a couple of possible distributions, I imagine I've got two variables. They both coexist. They both exist even before I've made my decision, how long my headache will last if I do or don't take the aspirin, Y1 and Y0. And the initial focus of this approach is on something called the individual causal effect, which is how much one would be longer than the other. How much longer will my headache last if I don't take the aspirin than if I do, say. But there's a problem which has been called the fundamental problem of causal inference, though I call it the fundamental problem of the potential outcome approach to causal inference, because it doesn't appear in my approach. And that's that these things can never be observed together. Y1 is what I would get to see if I do take the aspirin, Y0 if I don't take the aspirin. I can do at most one of those things, and therefore I can never directly observe this individual causal effect. I can never estimate its distribution. Fundamental problem, we seem to have missing data. Can somebody please admit the person who's waiting? Thank you. And that whenever that happens, I seem to get stuck. There we are. So as that can't be identified, the focus typically switches to the expectation of this quantity, called the average causal effect. And remarkably, that can be identified by a simple rule of probability calculus, which is the expectation of a difference is always the difference of the expectations. And if you think about it, I can estimate each term separately. I can estimate this term, that's how long my headache would last if I do take the aspirin, by considering patients who did and looking at their average, and similarly for those who didn't. So I can take those two things separately and take their difference. That's exactly the same quantity with different notation as I called average causal effect on the decision-theoretic approach. So we're back to square one, problem solved, or is it? So in a lot of problems like this, it doesn't really make a lot of difference which approach you take. The notation is different, the concepts are different, but maybe you end up doing the same thing. But I said, is the problem solved? Because actually, you can often end up doing different things. And here's an example. So something's happened again. Okay. Is there a chat I can maybe, there's a paper coming up in just a week's time. Will be, hello? Is it? Recording started and stopped and started. Okay. There's paper coming up. There's a, if you go to that website, you can get hold of the paper and all the details. You can even make a contribution to the discussion, either orally or in writing. It's a case to do with pretrial public safety assessment. And in different cases, what happens is they come for a pretrial assessment as a defendant, and the judge has got to decide whether to give bail, to require them to stand bail, or just on their word of honor as to whether they will appear at the proper hearing later on. And the outcome we're interested in is whether, well, that's actually whether they will fail to appear. So each case has background characteristics. They're particularly concerned with whether or not they should provide a score which is supplied by an automatic algorithm and for the judge to consider. But there's quite a lot in the paper. I'm not going to go through all of it by any means. One of the main things is what is the effect of providing this algorithmic score on the judge's decision and on the eventual appearance or non-appearance of the criminal or the suspect. Anyway, I'll ignore that for now and just concentrate on the simpler question. How ideally, if the judge has access to the background characteristics and possibly the PSA score, how should they use that to make the decision as to whether or not to insist on bail or just let them off with a promise to appear? So this is the order of things. First is background of the case, possibly a PSA from the algorithm. And now the judge has to make a decision. And then we have to wait and see whether the defendant turns up or not. And then will end up being a utility associated with that. So what can we do with the decision theoretic approach? It's quite straightforward. In the data and the assumptions made in the paper, this is quite easy to do. We can assess the distribution of the what is just a probability, will he or won't, probability the defendant will or won't appear at the next hearing, conditional on the evidence available and some hypothesized choice, because we've got a lot of data from which we can assess that distribution. And the decision theory says we just maximize the expected utility. So I consider what I do know, X and Z, the decision I'm hypothesizing, which can be 0 or 1, do or don't insist on bail, and what's the expected utility. And once we've got all the distributions, we think what utility is appropriate, and that's straightforward. So that's the simple decision theoretic approach. But in fact, a large chunk of the paper, which is up for discussion, takes an approach based on potential outcomes. And it goes something as follows. Again, we consider not one outcome variable, but two, because there are two possible decisions the judges can make. And there's a Y0 and a Y1. And again, we consider those as existing simultaneously, even before the judge makes his decision to decide which one of these will be uncovered and become actual. So if he makes the decision D equals 0, then Y0 will be the actual response Y, but Y1 can then never be observed. It becomes counterfactual. And conversely, if D equals 1, Y0 becomes counterfactual. And they then invoke an idea, quite a well-established idea now, called principal strata. Strange name, I think, for what we've got here, but there we are. But a principal stratum imagines that you can collect together all those cases having some specified values for this pair, even though you can never know of any individual the value of both of those variables together. So you can never identify who's in a principal stratum. So in principle, 4 possibilities. One of them is assumed not to happen. This is Y0 is 0. That means if you don't require bail, he will appear, and if you do require bail, he won't appear because this has failed to appear. And they say, well, that's just not reasonable, so take that out. That leaves 3 different possibilities, which will encode 0, 1, or 2, which they call the riskiness of the case. And they say the utility should depend not only on the decision I take, but also on the riskiness. I haven't got the outcome there, and that's because the decision and the riskiness together decide the actual outcome. But more than that, they also determine the counterfactual outcome. So this utility depends on both the factual and the counterfactual responses. And so the idea is that we choose D to maximize that, where we have the random variable, the random riskiness has to be assessed. The problem is that strong and untestable assumptions are needed to estimate that distribution. So I've just been through 2 different approaches. I think the simple approach is simple. I think the more complicated approach is complicated, and also frankly veering off in a dangerous direction. So my own questions are, is this sensible? Are potential responses meaningful at all? And if they are, in what sense are they meaningful? When do they exist? When do they coexist? Singly, jointly? And if they exist, if we can imagine they exist jointly, what assumptions about them are meaningful, and how can we assess their joint distribution, granted we can never observe them both simultaneously? And to finish, I'll go back to, well, are they relevant to decision problems? Go back to Glenn's questions to the panel. What are the obstacles to the adoption of my approach? A complete mystery. It's so obviously sensible. Why doesn't everybody do it? Is it more difficult to use in observational studies? No, it's actually very straightforward. Do standard interpretations generalize? I can't see why not. Why do some statisticians found counterfactuals useful? Mystery upon mystery. And finally, Glenn asked, can we assign responsibility for outcomes without using counterfactuals? I'm a bit ambivalent about that, but my ambivalent answer is no. Thank you very much. And that's the reference to the paper at the Royal Statistical Society.
Wow, well, thank you for a very efficient presentation, Phil.
Can I start? I got to try and stop sharing my screen now if I can.
Oh, you stopped.
I have, okay, good.
Thank you. And I'm not sure why we get, what the difficulty was when people were coming in, but hopefully that's calmed down. And Ilya, could you?
So I have the slides here, but is the format we just speak one after another, and then we have a panel discussion after everyone speaks?
So yes, I was going to ask each panelist to speak for 10 minutes, and then we have a moderated discussion, not a free-for-all, but can ask the panelists to ask questions of each other, and the audience can ask questions and make short comments.
Great, thank you. Can everybody hear me and see my slides?
Yes.
Great. I guess the title is a riff off of Philip's slide title. So I should say I'm sort of an aspiring statistician. I'm from a computer science department, but I have used graphs for causality for a while. I always viewed Philip's approach as graphical. So this is just a little background. Okay, so this panel is about the utility of counterfactuals for the practice of statistics and I guess empirical science. So we're discussing what are called potential outcomes, which are written y parentheses a, or that's the way I will write them, which mean the outcome y had a been assigned some value, possibly contrary to fact. In causal inference based on potential outcomes, as opposed to the kinds of causal inference methodology espoused by Philip, the outcomes for both hypothetical treatment assignments are presumed to exist simultaneously, and the observed outcome is obtained by what they call a coarsening process using the observed treatment, using this assumption that's sometimes called consistency or mechanism stability, I suppose. And my understanding of Philip's point of view is that functions of y1 and y0 viewed jointly, such as principal strata, but also other things that come up, such as probability of necessity, for example, should be cast aside. In particular, the principal stratum-based analysis of the PSA, which is going to appear in the red paper by Imai and collaborators, should be cast aside. I have a more moderate view, which I will attempt to describe. I certainly agree with Philip that I don't see the utility for decision-making or otherwise of principal stratum-based analysis in this particular paper. However, I do think that viewing potential outcomes jointly, so y1 and y0, can be conceptualized in some applications. I think there are very strong reasons to believe in their joint existence, if you like, and they could even be identified in some cases. I also wanted to draw a distinction between what I call an epistemic counterfactual, which is about someone's state of knowledge, versus an ontological counterfactual, which is about the state of affairs. And I think the former one is difficult to argue against, and I think arises in problems like missing data problems in statistics. And also, I just wanted to say that, statistics aside, counterfactuals, even difficult to evaluate via experiment counterfactuals, arise all the time in other communities. In particular, folks in physics think about them all the time. Okay, so since Philip discussed this paper, I will, and had a bit of a picture about it, I thought I would do my best job that I can drawing a causal diagram for what I think that analysis was about. So this is about setting bail for people who were arrested. And the point is, we would like to decide on the basis of how dangerous the person who was arrested is, whether they should be let out on bail or whether they should be kept in pretrial detention until their hearing. And the point is, we shouldn't keep people in jail unnecessarily, but at the same time, it looks very, very bad for everyone concerned if you release somebody and they recidivate. In other words, they commit a crime. And so the PSA was a set of scores that were developed by Arnold Venture. So in the interest of full disclosure, I am on their research advisory board, but I wasn't involved in the development of the PSA. And it's meant to assist judges with making decisions on bail in a useful way. And in particular, the PSA scores are very careful to exclude all of the stuff about sensitive features such as race from the information. Okay, so this is the picture as I see it. There are some background characteristics. A subset of those characteristics that are called X sub PSA are used to calculate these scores. And I think the study they looked at randomized whether judges had access to the PSA scores versus just general characteristics about a person. And the outcome here is failure to appear, which is a bad thing. But you could also look at other outcomes like recidivism. So this is my view of the graphical model. The PSA only affects the decision if Z attains one value. So there's a context-specific independence in this picture. And we want to evaluate the effect of PSA and D and or Y. That was my understanding of the goal of that paper, Imai's paper. So I think this design aims to get at what I would call the indirect effect of XPSA mediated by the summary scores that were developed by Arnold. And depending on whether judges get access to the raw values used to determine PSA, you could interpret the study as trying to get at the informativeness of these raw values. And so I agree with Philip that given that the goal is to understand if PSA is helpful for judges or if they can improve utility defined in some way, for example, utility that says that it's a priori bad to arrest people without reason or keep them detained, but also it's bad to have recidivism, then I could imagine the study just looked at directly as being pretty directly informative for that question without the need to involve principal strata machinery, which is very complicated, which does not correspond to the kind of thing that will help with individual level decision making at all, because we don't know principal strata for any person. I will say also that just as a side note, this is not directly relevant for this panel, but the decision to exclude features directly from calculating scores like this does not necessarily alleviate possible problems with race, because excluding something from consideration is an epistemic matter. You're essentially refusing to look at some data, but the causal pathway could still be operating. In other words, it could be that a race is influencing some downstream variables that may end up in XPSA, which may influence decisions. And so there are some ways of using causal inference methods to think about these issues using tools of mediation analysis specifically, but that's all I'm going to say about that. Well, so how plausible are joint counterfactuals? So Philip is not a big fan of them. So I myself come from the kind of Yuda Pearl land, although I like to think of myself as multi-paradigm these days. And so there are ways to go back and forth between the world of structural equations, which is the world that Yuda Pearl likes, and the world of potential outcomes, which is more popular in statistics and public health. And you could think of a potential outcome as the output of a structural equation if it were the case that some of the inputs of the structural equation were manipulable, and plus there is some exogenous noise term that makes the whole thing a random variable. Now, the reason this is interesting, this mapping, is that in some applications it is we know enough about the mechanism f of y and the exogenous noise term, and we know enough about it so we can conceptualize the joint outcomes, essentially. And indeed, this was always Pearl's point. Now, Pearl himself was an electrical engineer by training, and his examples were very much along the lines of circuits or computer code, where it's pretty clear that we could think about joint outcomes because the function is basically given to us. But there are there are other kinds of examples that arise. So this one is due to Dan Sharfstein, who I think is actually on this call. And this is from an unpublished manuscript that he is an author on, and there was a study, and the goal of the study was to understand the effect of UV exposure in the eyes of the study participants. And the intervention here was whether somebody wore sunglasses or not. And we know that if you wear certain kinds of sunglasses, that can reduce the UV intake into your cornea. And we are interested in comparing Y1, you wear sunglasses, versus Y0, you don't. And the interesting thing here is that the effect of UV radiation on your eye is something that has a physical model, is just photons hitting it. And there is a physical model that can get you one of the counterfactuals if you know the other, provided that we know something about the permeability of the glasses, basically. This is my understanding. So Dan will correct me if I'm wrong here. And I think I'm not going to say much more about this example other than to say that the cases where these kinds of models where you have detailed enough information to get at a joint counterfactual are not necessarily completely, uncommon. They do occur in the physical sciences and electrical engineering and so on. Now, it may also be the case, and Philip's point is well taken here, that these thinking about these things jointly may be harder to justify for some folks in public health applications where a lot of these causal methods are used. Okay, so counterfactuals are typically used to encode hypothetical states of affairs, had some different event taking place, but I argue that you can also think of them as encoding state of affairs had one's state of knowledge been different, which is a little bit of a different situation. And the latter type of counterfactual, which is what I call an epistemic counterfactual, often occurs in missing data problems. So for example, the example of an ontological counterfactual is the kind that Philip gave in his talk. I am a coffee drinker. I happen to have had coffee this morning, and I had some 10 minutes ago. And the question is, would I have a headache right now if I forgot or didn't have time to drink coffee? So this is an example of what I call an ontological counterfactual, where the state of affairs is changing. An epistemic counterfactual is something like, there is a survey, we ask people sensitive questions about their sexual history because we're concerned about the spread of HIV, which is a sexually transmitted disease, and people don't answer survey questions. And so the question is, what is the identity of their true sexual history, even if they left everything blank? And this is about our state of knowledge. So their state of, their sexual history is what it is, and the question mark on a survey doesn't really change that. And so I think there's been a pretty useful line of work that thinks about missing data problems. What would have happened if everybody answered all the questions? That uses this kind of counterfactual language that I think has been quite fruitful. I think I'm linking one of the papers that my students and I wrote recently, but there are many others that think of it this way. And I think these counterfactuals are quite straightforward to justify in terms of their existence. Okay. So this is basically, I'm almost at the end. Leaving aside epistemic counterfactuals, ontological counterfactuals have proven to be fruitful in causal inference methods. There's been a sophisticated machinery developed under the potential outcome formalism that tried to unify it with DAGs, and that's a paper on the single world intervention graphs that you can read by Thomas and Jamie Robbins, who is also on the call. Some of this machinery may be recast in a way that employs interventions, but eschews these kinds of counterfactuals viewed jointly. And so Philip has a very nice paper in the Journal of Causal Inference, and there are some accompanying comments, including by Thomas and Jamie, that get into this. Some statisticians and public health researchers that I've talked to are only willing to conceptualize potential outcomes of interventions are possible in principle to conceptualize as a randomized trial, and otherwise they're not. Of course, not everybody feels that way. So Pearl likes to say that many physical laws have a counterfactual formulation, even if you can't necessarily perform an experiment. And in fact, physicists sometimes entertain hypothetical laws of physics that are inconsistent with what we observe and are seemingly very happy to think about the result, like what the resulting systems are going to be like. It's unlikely that a trial will ever be possible here. I wanted to mention that the argument between Philip and folks who are willing to think about joint counterfactuals and causal inference seem parallel to arguments in interpretations of quantum physics, where one of the things that people, if you want to explain quantum mechanics, one of the things that you can give up is locality, which is sort of like their version of a local property, local Markov property, I suppose. And one of the things you can give up is the existence of joint counterfactuals, which I think they call counterfactual definitiveness. And that's something I don't understand enough physics to say more about, but I do think it's interesting that they seem to have similar arguments over there. My take on counterfactuals is I've used them quite a bit in my work. I found them quite helpful. And I think we should use it if it's helpful. And finally, I don't have any prepared slides, but because because Glenn has linked some questions, I can try to give my perspective on Philip's formalism. I think maybe so the first question is, why is Philip's stuff not used more? I think to some extent it's first past the goalpost. I think there's been quite a few folks who use graphs for causal inference. So Peter Spirides and Clark Glimor have written using graphs for causal discovery. Yuda Pearl has written a lot about this. There's been more recent work on Swigs. And of course, potential outcomes are very kind of advanced, mature formalism. And I just think it's a case of people being taught it a certain way in school without necessarily, so this completely ignores sort of the merits of the formalism. I don't find Philip's framework more difficult to use with observational studies compared to experimental studies. I think in my comment on Philip's paper, I do kind of a toy derivation that folks might find difficult at first glance, but I think it all kind of goes through. So I think you just kind of have to get used to it, but I find it equally easy to work with compared to other graphical formalisms I've used. I think statisticians find counterfactuals useful because people think counterfactually. I think I agree with Yuda Pearl on this. And I think that isn't exclusive to statisticians. I think it's true for scientists in general. And I think we just think counterfactually. It's very natural for humans to think that way. And I think, we have counterfactual connectives in English like had, because, and it's a short connective as well. It just indicates how easy we find speaking that way. I don't have anything to say about assigning responsibility for outcomes without using counterfactuals. I was quite fond of Joe Halpern's work in this regard. He uses structural equations, I think, in this work, but I'm not sure to what extent it requires counterfactuals considered jointly. And I think that's all I had to say about this. Thank you very much for listening to me.
Thank you, Ilya. Thank you very much. And I want to comment, I forgot to say that we are hoping for a good discussion session involving everyone who would like to, or as many people as possible. It would be helpful if you would raise questions in the chat, and we could try to take them in the order, questions or comments, and we could try to deal with them in the order in which they're made. We'll try to recognize raised hands also when we come to the discussion period, but that may be more difficult. And Snow will be helping me with recognizing people who have asked something in the chat. So our next speaker is Thomas. Take it away, Thomas.
Thank you. Can you see my slides?
Yes, but it's not full screen. Maybe that's intended.
That's intended. Clark has raised his hand. Clark, can you raise your hand? Reason for that?
No, I'll wait till the end.
Okay.
I'm just getting
Okay.
in.
Okay, getting in. Okay, great. Yeah, so I just want to start out. I sometimes do this in my course. Potential outcomes, I think, do arise very naturally in many contexts. I mean, one example that they came up, this was a UAI paper some time ago, civil engineering criteria for setting speed limits. So US traffic engineering practice gives preference to the 85th percentile of vehicle speed distribution. If that's above the posted speed limit, then the speed limit can be increased. But there's a condition in the regulations which says unless there are accidents that would have been prevented had the speed limit been obeyed. And so civil engineers gather data on accidents that occur in places where we want to put the speed limit up. They take the length of the tire skids, the before and after impact, the distance the pedestrians throw, the severity of any injuries, and then they construct a sort of complicated model that can be expressed as a graph in order to work out a distribution over the probability that an accident would have happened had the driver been going at the speed limit at the instant that they saw the pedestrian. So yeah, so you know, civil engineers don't seem to be a fairly sort of down to earth and concrete consider decision problems they deal with, and they definitely are using potential outcomes in their context. I think potential outcomes also come up very, very naturally in statistics, in, for example, testing the Fisher-Sharp null. I mean, this is you know, as all of you probably know, the Fisher's lady tasting tea example, basic idea that we observe some set of experimental results for a treatment group and a control group, and then we want to ask the question, well, if being in treatment versus control would have had absolutely no impact on the outcome, how likely would we have been to see a difference as large as the one that we observed? And there's a very natural randomization distribution. I just think you know, this leads into finite population randomization-based inference, which really seems, you know, I would be extremely averse to any agenda that was going to rule that out as a method of inference. You know, it seems to me that this is just a very natural way of thinking about a data analysis, a causal data analysis, where you simply want to say, you know, this is a very natural and intuitive null hypothesis that our treatment is having no impact at all on what happened. I think that's intelligible to absolutely anyone, regardless of whether or not they, you know, almost with no ontological commitments. And then it's natural to then think about the randomization distribution. And the great thing about this kind of inference is it doesn't require any assumption of there being an infinite superpopulation, or doesn't require the people that are participating in study to have been randomly drawn from any other set. And you know, this is important because, for example, in a randomized clinical trial, participation in that trial may involve stated and unstated criteria, like, you know, having the time to participate in the trial, or, you know, wanting to earn extra money by participating in the trial, or all sorts of other criteria that may make it very hard to generalize the results from a randomized experiment to a larger population. And so randomization, finite population randomization-based inference, you know, just leaves all of those questions to one side and just looks at testing causal effects within the people that actually participated. Okay, talking about, so this was not so central to Philip's presentation, but it is implicitly there is along with the decision-theoretic approach that Philip has presented, he has a graphical representation for that. And I don't have time to outline all of this here, but basically it's not hard to translate between the representation that Philip has. So for example, this is up here, this is a simple decision diagram we've had with a single treatment and a response. Philip has recently, in his recent paper that he referenced, he's extended this to now include an intent to treat variable, which is describing the sort of the natural value of treatment that somebody would receive in the absence of intervention. And over here we have there's a swig representation. I don't have time to show all of this here, but essentially it's possible to map very simply backwards and forwards between Phillips representation and the Swig representation. I'll show you one other example here that you may be familiar with, the front door graph. If I show you that here, so here's the front door graph, and this is the front door graph. Before we do any interventions, this is the Swig representation. This would be Phil's decision diagram. And then if we just marginalize over this t variable, we end up with this graph, which, as you can see, without going into any of the details, you can see it's very, very similar to the graph that we have up here. This red little t is corresponding to this square box here. So yeah. So in a certain sense, in certain ways, the recasting, the way that we've recast Phil's approach also allows us to more fully derive the Markov property. So the graphs that Philip has given have dashed edges, and those dashed edges are context-specific independencies, so they disappear when you condition on certain specific values. But the defining Markov property that Philip has set up doesn't actually directly imply those. They would have to be added later. Anyway, at a high level, given that the distinction between these two theories, given that these two theories are isomorphic, the distinction between them really seems to be one of taste and notation rather than actual identification results or metaphysics. I should say here that the potential outcome approach that we developed in order to make it isomorphic to Philip's approach, is minimal. So we dropped the usual consistency assumption that's used in potential outcomes, and instead just have a much weaker distributional consistency assumption. Okay, Philip. As I mentioned, he's introduced these intent to treat variables that tell us the value of treatment that the patient would take in the absence of intervention, and those prior to sort of treatment being finalized. And I will say the existence of those variables seems to me to imply that the units in a hypothetical population where everyone receives control and units in a hypothetical population where everyone receives treatment could live on a shared probability space, because if we have a natural value of treatment that is being realized before we decide what value of treatment people actually get, then it seems to be there's no reason why we couldn't put all the units onto one probability space. We don't have to, but I don't see why Philip's approach. It seems unnatural in Philip's approach not to do that. I'll sort of say this quickly because Ilya already commented on this. There are also situations where hidden variables and potential outcomes are sort of, in some sense, equivalent formulations. And in fact, Philip did this, it came across this in that he derived the bulky Pearl bounds for the average causal effect in the instrumental variable model. And he didn't explicitly use potential outcomes, he just instead used latent variables, or equivalently stochastic counterfactuals. But if you look at the details of Philip's proof, it ends up considering extreme points of the latent variable model, which correspond mathematically to deterministical potential outcomes. So I think this also tells us that in a certain sense, potential outcome models can be viewed as an abstraction or coupling that give insight into possible causal models, even if one doesn't wish to assume deterministic potential outcomes. I'm going to make a quick comment here, which is that in some ways, it seemed to me that the reluctance of people to have deterministic potential outcomes and instead wishing to have stochastic potential outcomes. So sort of, Don Rubin had the story that potential outcomes, each person has these two playing cards on their forehead and they sort of show the playing card corresponding to the outcome for the treatment they receive. And I've often thought that the stochastic potential outcome, we sort of instead have two random number generators on our forehead, and then we then press the one corresponding to the treatment that we see. It's often seemed to me that in a certain sense, that's a rather similar move to the move that's done in fuzzy logic, where people don't want to say that statements are either true or false, and instead they assign a number to those statements. And in some ways, that seems to be analogous to what's going on with stochastic potential outcomes. So it's also similar to, in statistics, we have discrete latent class models that say everyone is a member of a particular class, and then there are other models that sort of grade of membership models that say people have some percentage of being in certain categories. Okay, principal strata. So these came up earlier. I think that they do arise very naturally in some contexts. So for example, if we want to talk about what the survivor adverse causal effect, so suppose we've got two medical treatments, and then we want to see, if assuming that people survive the procedure, we then want to see what's their quality of life like, then in a certain sense, it only makes sense to compare the effect of the two different treatments on quality of life among people who would survive under both procedures, assuming that we're not going to assign a quality of life to people who are dead, which seems a little unnatural. Equivalently, effect of vaccination on post-infection endpoints. We can't look at, say, someone's viral load if they didn't ever get infected. And I should add here, there are cases where principal strata completely unproblematic and has no metaphysical problems whatsoever. And this is going on daily in big tech companies, because in big tech companies, they're often doing experiments where they are changing some aspect of a complicated algorithm. And then they're seeing how someone on the website is then responding to that algorithm. And so often the complex algorithm, it's like the example that Philip had with the judge, except instead of it being a judge who decides whether or not the person gets bail or not, and then the person responds, there's an algorithm that is, instead of granting bail, it's recommending you something to watch on Netflix, for example. And there may be two different versions of that algorithm. The people, it may be the case that if you make a small change to the algorithm, for many people, the recommendations that are being made to them won't change at all. And so in order to see the effect of changing on the algorithm, the tech company will run the algorithm, will run both versions of the algorithm for each user, and they will then see for which users is it the case that the recommendations are actually different. So essentially, they restrict to a particular principal strata, and this is called counterfactual logging. So there are situations where I think there's no argument this can be used. Okay, I'm on to my last slide here. So I think causal graphs of potential outcomes are rich languages, and they have great expressive power, and they allow analysts to understand complex situations. They complement one another, and by causal graphs here, I'm really talking about causal graphs that sort of non-potential outcome causal graphs. I don't think either subsumes the other, and I think frameworks can be misapplied. They allow, within both frameworks, you see people formulating identification assumptions that are opaque or hard to verify, or hard or impossible even just to falsify. I certainly agree with the approach of trying to formulate causal models that don't force modelers to make untestable assumptions. I think that was present way back in the causation prediction and search book that tried to take a kind of agnostic approach to formulating causal models, and I certainly think that I'm very much opposed to the procedure that you see sometimes where sort of causal graphs are presented in such a way that independent errors or individual level exclusion restrictions are the default. And the naive user is sort of suggested that they get magical identification results merely from writing down a graph. I'm not happy with that at all. On the other hand, even if I don't think people should be making independent error assumptions, or they, assuming cross-world independence of counterfactuals, or assuming individual level exclusion restrictions by default, I certainly don't think that that we should prevent people from ever making those assumptions, because there are circumstances where we do have very strong background knowledge, like the car accident example I showed you, like the examples in the tech company where they can see both the potential outcomes, like situations where we run a randomized trial and we know that there's no problem with compliance in the control arm. So I think there's basically a rule, which is whenever a methodologist says this can't possibly happen, there's no way we could measure that, this is meaningless, then it's almost a sort of law of nature that within a very short period of time, an experimentalist will come up with a way to measure that and prove the methodologist wrong. I think that's, just to answer Glenn's questions, I think reasons that the decision-theoretic language hasn't been used in statistical practice, I think that is partly because the potential outcome framework reduces causation to missing data. And I do take slight issue with what Ilya said here. So Ilya was distinguishing between kind of missing data potential outcomes as not problematic and versus counterfactual outcomes as being problematic or more problematic. I think there are situations where missing data can certainly be highly problematic. I mean, you know, if you're trying to call up someone to ask their opinion about something, and you don't get hold of them on the telephone, and the reason you don't get hold of them on the telephone is because they're watching a TV, they're watching information on TV that's changing their opinions as they speak, then it's not at all clear that this missing data is uncontroversial. Is David's framework more difficult to use with observational studies than with experimental studies? So I mean, I do think that there are contexts like there isn't a way to formulate the principal stratum analysis, and I do think there are contexts where that is meaningful. Not every context, but there are some. And I do think that the way that the instrumental variable analysis that Philip did, I thought did require a fair amount of work, though Pearl's original analysis also required a fair amount of work in computational algebra. But I do think that in some ways, yeah, ultimately, given that the proof involves potential outcomes anyway, it's not really so clear what's gained by doing that. Why do some statisticians find counterfactuals useful? I think because they are, you know, because they're fundamental to an awful lot of human reasoning, and there are certainly situations where we do have models of the world that are detailed enough and accurate enough for us to be fairly confident about counterfactual predictions. Can we assign responsibility for outcomes without using counterfactuals? I would say probably not. Stop there. Thank you for inviting me.
Okay, well, thank you very much. Let's hurry on and have Sylvia tell us her thoughts so that we can have time for some discussion.
Okay, thank you. With me, it's going to be very much back to basics for two reasons. One is that I'm new to this debate, and the other one is that I will actually focus on probability. So I will look at the aspirin example again, which we saw presented at the beginning. And yeah, I will see how far we can get. Obviously, I won't get into details of statistics with this method, but I wanted to start with basics because the first question is, what is the sample space? So here we have all atomic possible outcomes. So when we observe any of these, we know that all the others are contrary to them. So all possible outcomes are, yeah, they are mutually exclusive. So whatever we are going to observe, it will turn the other options that were there initially into counterfactuals. So maybe that will be important later on. Now with the simple example where we are only thinking about people currently having a headache or episodes of headaches, we can make a partition of the sample space into those people who take an aspirin and those who don't. And later on, maybe after 30 minutes, we can make yet another partition of the same sample space, and the same elements are now divided into two sets, one where the headache has persisted and the other where it hasn't persisted. And obviously the probability assignment will be such that these sets have different measures. So I just indicated one possibility, and here you have all the partitions at the same time. We're indeed taking
Sylvia,
yes?
Sorry, your slides are not advancing. I just wanted you to know that.
Oh, that's not a good thing. Thank you for telling me. I will try again.
We're seeing your other screen.
Let me try that again. So you always saw the same slide from the start?
Yeah, with the ones on the left.
Okay. Can you now see a more complicated slide? Okay, I hope now it will advance. Yeah, so I just filled in some numbers for a case where indeed taking an aspirin would make the probability that a headache goes away bigger than for those who don't take the aspirin. But obviously the whole point of statistics is that you don't know these values. You're interested in more complicated distribution, etc. But this is the general idea of probability, that you can represent them with sets, the different events. And if you have a depiction like this, where the area is indicative of the probability, that's called an Euler diagram. But obviously, if the questions are about causality, something is missing here, because at least you would like to take into account, like, what is the order of the events, so a temporal order. So maybe we should look at other depictions of the same information. An obvious choice is, of course, an event tree or a probability tree, where the exact same information could look like this, but we have already a clear picture of the order. Now, this kind of depiction actually also is suggestive of a stochastic process. It doesn't have to be, but it's suggestive of that. And that reminded me of a third option, again, the same information, and I call it meticulous style, referring to Euler and Albert, who actually take their inspiration from statistical mechanics. So what is the idea here? This is actually perfectly compatible with the deterministic scenario, where there are different people who may not know all the details of their body, and they don't know what they are going to do in the future, but some of them will end up taking the aspirin and others won't. And later on, the headache will or will not go away. So here you can sort of see the connection between the temporal order, which is one part of thinking about causality, because the causes should precede their effects. But on the other hand, you could sort of imagine viewing it from the side, and then you would see the exact same sample space as before. But now there's sort of added information about the microhistories of these different points of the events. So these were just some very basic ways of representing the relevant probabilities. Now let me turn to some of the relevant probabilities for the case at hand. So on the standard view, obviously in the sample space, you can read off conditional probabilities for persisting headaches, whether or not you took an aspirin and all those things. They are sort of laid out there, existing simultaneously. I'm not sure if that is already problematic, but in any case, it will always be such that if you can observe one part of the sample space, that excludes sort of by definition of how a sample space works, simultaneously observing any other part. That's built in from the start. That's a very basic thing. Now, it also means, I think, that in principle, in general at least, all these conditional probabilities can be completely unrelated, and they don't define each other because they are simply about different parts of the sample space. Now, I read one of the earlier papers by Phil Dawid, and there he made a point out of, for instance, you can be considering all these probabilities and matters of causation sort of beforehand or without being in the picture, so to speak, or you could know that you have taken an aspirin, or more generally, that the person of interest has in fact taken an aspirin. There was a discussion that now we can take this conditional probability, conditional on having taken an aspirin, in the indicative mood. And that at that point, of course, not having taken the aspirin is a counterfactual. Now, I had the impression that what was going on there could be understood in terms of a Bayesian update. So at that point, you really constrict or restrict the sample space, which was initially larger. There were other possibilities, which have now become counterfactual. You exclude them and you re-normalize your probability function on a subspace of the sample space. And obviously, in such a case, it's true that on this new probability function, which only takes non-zero values on a smaller part of the initial set, that the probability of not having taken the aspirin is now 0, and that conditional probability associated with that event is undefined. So I was thinking that perhaps that could help connecting it to other parts of the literature, phrasing it like that. And then a final comment or thought was in terms of what in the end, how are we going to measure this causal effect? We are going to compare certain probabilities. So this discussion reminded me of various proposals for measures of confirmation or support of hypotheses by evidence. This is not in general about causality, but there are counterfactual measures there. And I do think there is a symmetry there. So also in that literature, there is a lot of arguments for and against these measures. There are certain adequacy constraints, but none of these measures fulfill them all. So I was wondering if more could be said about this analogy. It's not exactly the same thing because here we are talking about confirmation for a hypothesis. So it's sort of at a higher level than simply the probability of having a headache after having taken an aspirin. The hypothesis here would be something like taking an aspirin probably causes the headache to go away. So you're talking at a different level. But I did see a similarity there. So these are my comments, not as advanced as those coming from the statisticians, but I hope still there is some common ground to discuss further. So thank you.
Well, thank you, Sylvia. We'd like to, let's see, I'd like to have some discussion now. A lot of this was disagreement with Phil. I think I should give Phil a couple minutes to comment on what what he would most like to respond to.
Thank you, Glenn. Actually, I mean, I think, you've chosen discussants with whom I probably have much more agreement than most other people who work in this area. I tend to agree with Thomas in particular that the Swig approach, which he and Jamie have pioneered, and my approach are essentially isomorphic and slightly different ways of doing much the same thing. We're certainly motivated by the same philosophical commitments. A couple of points about a lot of the examples to try and convince me that counterfactuals often can exist. These are essentially those where we have a deterministic or pretend we have a deterministic understanding of the problem. And again, I think it's relevant, the comment was made that Euler Pearl comes from electrical engineering and computer science, where deterministic relationships are quite natural, as they are in physics, but they're completely unnatural in most applications in, say, the health sciences or the laws we've had today. And therefore, when you have determinism, yes, okay, you can understand what counterfactuals are because you have laws which tell you what would have happened under hypothetical circumstances. But that's not the same, I think, when you don't have a deterministic understanding. One specific point that Thomas mentioned about Fisher's null hypothesis. Fisher's utterances are always incredibly gnomic, and they're like the Delphic oracle. I have tried to read what he said in the response to Neyman and other places about his null hypothesis, and I do not actually agree that what he was saying is necessarily that he meant that he was dealing with potential responses. I think you can interpret it that way if you want to, but you can interpret it in other ways as well. And in fact, you don't need that interpretation to do your randomization experiments or analysis. Assumptions of exchangeability, for example, which are purely probabilistic, will get you to the same endpoint. Another point I'd like to make is it's often been said that the potential outcome approach is a much richer language than my decision-theoretic approach, and that's certainly true. I think that's a danger because it enables you to say stupid things. That there's no obvious clear boundary between there are lots of things you can express in the notation, some of which are perfectly sensible and to my mind, and others which are completely stupid. And there's no clear boundary which you have, when you're overstepping it. So I would actually make an analogy between the decision-theoretic approach and George Orwell's Newspeak in 1984. Newspeak was a language which was specifically constructed by the state, in which it was impossible to express criticism of the state. In other words, it was impossible to do what the state considered as stupid things. And likewise, I think that the decision-theoretic approach protects you from doing stupid things, which the notation of other approaches like potential outcomes or graphs with independent error variables do not protect you against, and you don't know you're doing something stupid. I'll leave it there. Oh, and thank you, Sylvia. There's some interesting points there. And I'd particularly be interested actually in if Glenn has anything to say about your decision tree representation of the problem.
Well, I won't jump in on that, but let me ask who else would like to comment. I see Clark did raise his hand a long time ago, so what would you like to add here, Clark?
More subtract, I guess. I would like to probe a little bit Phil's philosophical viewpoint. Aristotle asked, is it true or false or neither today that there will be a sea battle tomorrow? We can modify his question a little bit, as in, if we send out the fleet, will there be a sea battle tomorrow? If we don't send out the fleet, will there be a sea battle tomorrow? We might have experience about the frequencies of sea battles and so on. Is it that you object to counterfactuals, to counterfactual variables, or to only probabilities assigned to counterfactual variables?
Oh, I can answer that very easily. I object to the counterfactuals in themselves, even before we come to modeling them.
So,
but I'm very happy with hypotheticals, things which happen, things which I consider in a hypothetical state, which is possible to bring about, but not necessary to bring about.
So if I could continue just a moment, we can't change the past. So is it, on your view, neither true nor false that if we had sent out the fleet, there would have been a sea battle yesterday?
I mean, I think it's a good question. I think I would say it's neither true nor false.
Okay, all I asked for was clarification. Thank you.
Maybe before I ask for other comments, we could retrospectively say what, if we think of probability as predictive, we could give probabilities for whether that would happen retrospectively. Given what we know now, what would our best prediction have been then? Would that be reasonable for you, Phil?
Sorry, the problem there is that we actually know that, say that there wasn't a sea battle. That's part of our knowledge today, and therefore, do we condition on that as well? And in which case, the answer to any such question is no, there wouldn't have been a sea battle because I know there wasn't.
No. We could make.
If you're saying I condition on information I have now, it's reasonable to say, put myself. Sorry, let me finish this. It's reasonable to say, let me put myself in a historical situation where I was then with what I knew then and what I could assess then. That's fine. I could assess different things then. But now I know the outcome. I know yesterday that I know there was no sea battle.
No. What I mean is, we could retrospectively say, now that we saw what happened, given the decision we made, we could say retrospectively, what would have been my best prediction then about the results of a different decision. We could give probabilities for that. We can't. It would be one thing to say that such a thing, such a fact exists, but there would be another thing to say, well, here was to be the best prediction we could have made under that circumstance in that situation, given what we know now.
Yeah, but given what we know now, it does make it very problematic. I mean, you say I took the aspirin and my headache went away. Would it have gone away if I hadn't taken the aspirin?
Well,
can I assign a probability? Can I assign a probability to that? Well, I know it went away, and therefore that tells me something maybe about all kinds of hidden variables, my frailty, other things which aren't part of, and those can be fleshed out in so many different ways, all consistent with observation, and are consistent with statistical knowledge. That you end up with, well, you can sometimes get bounds, but you can't get exact answers typically to that sort of question.
But it would make sense to asking that question wouldn't commit you to saying that there exists a true answer to whether it happened, whether it would happen or not. It would just, well, what have been your best predictions in those circumstances?
I mean, let me go part of the way. I mean, as you know, I've also worked on the problem of understanding causes of effects, for which, rather against my better nature, I've essentially had to use potential outcomes in order to phrase the question. But I do so, perhaps this is an example of what Ilya called epistemic counterfactuals. There are things I can think about, but don't really believe have a genuine existence, that they're part of a sort of fable I tell myself. Well, let's leave it at that.
Okay, the Snow, who's got the next question? Do you, or
so I think
comment?
Ryan raised a bunch of comments in the chat. So I don't know whether or not Ryan would like to talk about the comments. That's the only comment I saw, actually. So if anyone else has any question or comment that I missed, please feel free to just repost them on the chat, and then I'll talk.
Yeah, I mean, I'm happy to speak up and pose the same, questions that I posed in the chat. I mean, the first one is, I have a substantial interest in applications of causal methods, right? And at least the first two talks kind of said that there weren't really good uses of principal stratification. So I was just curious if anyone had a counter argument that there's actually a good motivating example for when principal stratification would be reasonable or suitable to use.
Did Thomas raise his hand to respond to that, or I see?
Yeah, I did. I mean, I think there definitely are circumstances where principal stratification makes sense. Yeah, I gave a few of them. I think that trying to work out I mean, first, they're being used. I mean, you can look up textbooks on how to run A/B tests. They'll talk about counterfactual logging. I mean, we can say, well, those are just deterministic systems, which is why people are doing it. But I mean, there are absolutely situations where we get to observe both the potential outcomes. So, you have, as I say, if the judge is not a human, it's a neural net, and you have control over the whole thing, then you can find out what's the decision that the judge would have made. The recommender system would have made given two different inputs, and so you can find out both the potential outcomes, and then you can restrict attention to the people for whom the treatment would have made a difference. So it's just and that people do that because they want to, because restricting attention to those people for whom the treatment actually does create a change in the intermediate variable is is going to give you much more power to detect whether or not what is the effect of that change by restricting to those people. But I mean, yeah, I also think survivor average causal effect, and when people when they were looking at the HIV vaccines and the vaccines didn't unfortunately didn't prevent people getting infected with HIV, but then there was some evidence to suggest, I mean, not very strong evidence, but there was some evidence to suggest that among people that got infected, those that were vaccinated had less severe disease than those who weren't. I mean, this is something I guess we're all familiar with, right? At this point, this is what we're all being told. I mean, I'm sure correctly, that that being vaccinated, it's not going to prevent us getting infected, but if we do get infected, the disease will be more mild. If your outcome is what's your viral load, doesn't really make sense to talk about viral load for people that never got infected. So that, you know, that outcome is not well defined unless you have been infected. So you can only talk about a difference amongst people that would get infected under both treatment and control. Just the same as quality of life for people that didn't make it under one of the surgical procedures. That seems kind of hard to evaluate.
I think that's a good point, but I would never know those people, right? So if I'm faced with a patient and I need to know whether to treat them or not, and I have just the survival average causal effect, I don't know if they're one of those lucky people that would survive regardless of treatment or not. But shouldn't that factor into the calculus of what intervention to assign them?
Well, I mean, A, you could try to come up with models that are good at predicting which strata people are in. People do that. And B, you know, you take one problem at a time. You work out what is the effect, right? I mean, you got, if the two treatments have the same survival rate, but you then want to look to see are people doing better under one than under the other. I think that's a meaningful thing to look at.
Why isn't it good enough to look at the difference in expected values, as Phil was talking about, or the difference in probabilities, rather than saying that there is some true value for the result of the opposite action?
But in the infection case, the random variable is not well defined. Right? If somebody's not infected, they don't have a CD4 count. It's not a CD4 count, they don't have a viral load. So the response variable just does not exist for people unless they, so you would have a measure of something in one arm. It's the same thing as, you know, if you're not willing to assign quality of life to people that die, then you don't have there is no value that you can measure for the people that don't survive under one treatment.
Thomas, can I ask you or make a remark about your isomorphism result? It's comforting, but it's still the case that when formalisms are proved equivalent, different investigators may differ about which features of which representations are real. So to take an historical example, von Neumann proved the equivalence of matrix and Schrodinger versions of quantum mechanics, but Schrodinger still thought there were probability waves. So it seems to me, despite the equivalence that you show, it's still quite possible to have very different views about what attitudes one ought to take to portions of the formalisms. So I think Phil's position is still quite consistent, even if odd. Never mind, Phil, I take that back.
What's odd about it? It's completely natural.
Not odd at all.
Thank you.
Do we have another person that wants to comment?
Yeah, I just wanted to say something briefly about one context where I found Philip's way of thinking about causality useful, which is paradoxically the one where the setting where the usual assumption Philip makes failed to hold. And so for Philip, you have these reified decision nodes that point to treatments. And, you know, those are used to encode, you know, things like conditional, what we call conditional ignorability in causal inference. And I found the existence of those nodes helpful for thinking about kind of exotic causal situations, such as ones you might use to encode Newcomb problems times things, where basically, you know, you're playing against an adversary, and the adversary can read your mind to a sufficient degree that they could figure out what you're going to do tomorrow, and on the basis of that, they put something in the box. And so the way one could encode something like that within Phillips formalism is to just add additional edges to the reified decision node, the ones that you wouldn't ordinarily add. And so I think there are, there's certainly, you know, I haven't found an easy way to think about that in the usual potential outcome language, but maybe I should revisit that given Thomas and Jamie's recent comment, basically, since isomorphism being what it is. But yeah, I did find it helpful, and I do think it is perhaps simpler to teach. So I also try to teach causal inference to undergraduates, and I can tell you that a typical computer science undergraduate who may have had a machine learning class before does not have an easy time with potential outcomes at all, because it's really not something they are accustomed to thinking about. So.
Let me try once again with Thomas, with my own sort of reaction to this. It seems to me very strange to, you know, assume that with all the contingencies in the world that, you know, somebody that wasn't infected, we could predict what their viral load would be. And I may be mixing up the things Thomas was saying. So anyway, but if this is the picture, say, where you want to say, if someone had been affected, what would be their viral load when they weren't infected? I could imagine saying, trying to make a conditional prediction, probability prediction for that. And if I made it for very many people, you could test whether I was a good probability predictor at that. But that wouldn't entail, you know, if I made that a lot of predictions, you know, and other predictions, you could test my performance as a probability predictor. But that wouldn't mean I was committing myself to there being an exact true answer to it, because there's so many things that could determine what the answer was that I don't regard as determined in the world. Doesn't that make any sense to you?
I think you're getting two points that are confused. So essentially the issue here is not that we're trying to predict what the viral load would be for people that didn't get infected. What we're doing is we're saying that if we're looking at the effect of the treatment on viral load, and viral load isn't defined for people that never got infected. So you might be, supposing that you, for example, suppose that you weren't vaccinated, let me just finish, suppose you weren't vaccinated, but you, and you got infected, and you have a viral load. And suppose that we have some sophisticated model that whereby we could work out that had you been vaccinated, you wouldn't have had a viral load. You would have never got infected. So in that case, for you, it doesn't make sense to talk about the effect of, I mean, it's a much more clear-cut case in the situation where, say, you know, suppose that there are two surgical procedures and we give you one procedure and then, you know, you go on and live a happy life afterwards. But then supposing we discover that for whatever reason, maybe there was some allergy that we didn't understand at the time or some adverse reaction, had we given you the other treatment, you would be dead. Then it wouldn't make sense for us to talk about the effect that had on your quality of life, because you wouldn't have had a life if we'd given you the other treatment. So it's that particular circumstance that's being addressed. And the issue that Philip has is whether or not it makes sense to think about a subset of the population, who would survive under either treatment, or the subset of the population who would be infected under either treatment. Because for the reason that Ryan was just saying, in general, we're not going to know who those people are. But on the other hand, we can do inferences about it, and we can sometimes compute bounds. You know, we can work out, well, for example, you know, we can work out we can look at the outcomes that we see among the people that were in the treatment arm who did get infected, And then we can then work out, which of those, which of those people would have also got infected under the other, if they had been in the other arm, and we can come up with worst case bounds, for example. That's not necessarily going to be point identified, but we can come up with worst case bounds. And I mean, yeah, and I think there's a sort of
worst case bounds with some probabilities.
But I mean, essentially, we're looking at distribution of outcomes, and then we're saying that people, this distribution of outcomes is a mixture of, say, two different types, and then we can then work out, well, how do we divide up those outcomes amongst the two types?
Okay, I'm sorry, I have taken up some of our very little time, and there were several people. Snow, who's next?
So I guess Ilya has a couple of points. So I wonder if, I don't know whether Ilya wants to talk about the comments that he made in the chat. And after that, I think Zhehui also has a question.
Okay, let's try to get those in before we end.
So, I mean, I was just responding to what was in the chat, if that's what you meant. No, I think the question was about 7 tests for utility of something, right? And I guess so there was a very similar discussion during the opening workshop. That's what so I can expand on that a little bit. So I think people were discussing, like, they do calculus and all of this machinery for dealing with causal models with graphs, and somebody was asking, like, how that's being used. And I think when people ask these questions, they're often like implicitly in their heads, they're thinking of something like a support vector machine or a neural network. Can I get better performance out of my benchmarks or something? Is it more useful in practice? But I think what is being discussed here it's a bit of a type error to ask those kinds of questions of what is being discussed here. I think what's being discussed here is a way of thinking and possibly a formal deductive system. And so I think a better analogy from computer science would be like theory of NP completeness by Cook and Levin, which a lot of these bullet points wouldn't apply to, like, exactly, right? You can't say that theory of NP completeness directly improved the performance on benchmark problems, but of course it was incredibly influential and led to very useful ways of solving previously computationally intractable problems, because people now understood that there are serious obstacles, and they started, creating, for example, very fast satisfiability solvers, which are now used in all sorts of applications in computer science. So it's sort of indirectly, the effect is very big, but directly perhaps not. And I think a lot of this machinery is the same way. I think it really incentivized a lot of subsequent developments. And I'm just talking about just generally thinking about causal models using graphs, not necessarily singling out any one particular formalism here. I think at the end of the day, we agree on most things anyways. I think we're discussing about a very small set of things compared to people who don't think that causality is real. Sorry.
So Jay, I guess you have the last word if you could make your comment.
I'm not sure it's me. My name is Zhehui Luo. I think Ilya was responding to my question in the chat. It was from a brief comment by Andrew Gelman in the book of The Past, Present, and the Future of Statistics. He was talking about the dilemma of pluralism. What do I do when I have so many different models? And I think no matter how philosophical our debate is today, eventually something should pass some sort of test in reality. I'm just wondering if anybody had investigated from that perspective.
I'm sorry, would you ask your question again? I didn't hear it.
I'm sorry, my question is not really my question. I think my question, Ilya said I asked the wrong question. So I'm not my understanding of today's debate seems to be off, which is this question about how do we decide to believe in the effectiveness of a statistical method. But I want to sort of use analogy and say, how do we decide to believe which one of these approaches is more effective?
I think that depends on whose hands they're in.
Maybe we should ask Phil if he wants to comment on that as our final final comment of the evening.
Yeah, well, I mean, Euler Pearl keeps on saying that all these different approaches are essentially isomorphic to each other. And it's clear that that's not true, because there are things that can be said in his kind of approach, which I can't say and I don't actually want to say. And so I'll just repeat the point that I made earlier, that I think if your language is too rich, you may not be able to tell when you have phrased a sensible question from when you have phrased a silly question.
Okay, well, thanks much, everybody. I hope this was, I think I learned something and learned that there's a lot of things I don't understand in what's going on now. And I hope next week we will be equally informed. Thank you very much, everyone.
Thank you, Glenn.
Thanks for organizing it. And thanks
for organizing this.